Softmax is one of the most commonly used functions in deep learning, especially on the output layer of a multi-class classification model. Softmax is really the sigmoid's older sister. If you haven't watched our video on the sigmoid, I will link it above. Please go ahead and watch it and come back. In our video on the sigmoid, we've explained how the sigmoid is used as an activation function to convert predictions into probabilities in a binary classification setting where we want to predict if something is true or false. So for example, if we had an image like this, and we wanted to predict if this is an image of a cat or not. So what we did last video is that we passed the pixels of the image into our cat classifier. We did a linear transformation, W transpose X, and then we applied our sigmoid function to that output to convert it into a probability between 0 and 1, which means we have a binary classifier that says if this is a cat or it's not a cat. Now, in our new setup, let's assume you want to do multi-class classification, where you want to classify if this is an image of a cat, or is it an image of a dog, or is it an image of a bird. So let's assume we have only 3 classes that we want to predict, and we have an image, and we want to know, does this image represent a cat, a dog, or a bird? And this is exactly what multi-class classification does. So you can imagine a multi-class classifier in its simplest form as a bunch of binary classifiers stacked together, and each of those classifiers is predicting a certain class, the probability of this image belonging to that class. So for example, as we have done in our previous video, we will take our image and vectorize it. So we will have pixel 1, pixel 2, all the way to pixel m by n. Then I'm going to pass my inputs, the vector x, into all of those binary classifiers really stacked next to each other, and each classifier looks exactly something like this, and it will generate a probability of this image belonging to a cat, the probability of this image belonging to a dog, and the probability of this image belonging to a bird. Right? So we have, instead of having one binary classifier, we have stacked 3 different binary classifiers next to each other. Each classifier, so we have a cat classifier, we have a dog classifier, and we have a bird classifier. And each classifier is generating a probability of this image belonging to a cat, a dog, or a bird. Now, the question is, what function can we use on the output of this multi-class classification model? Can we just use a sigmoid function like we have been using in our binary classifier fashion? What happens if we use a sigmoid function? Let's see. So let's represent this network in a vectorized way. Well, first of all, let's remember how our binary classifier used to look like. We said that it is nothing but a linear transformation, W transpose X, and we call that Z, and then we will apply the sigmoid to the Z. And we said that Z is a scalar value. It could be -1, -2, 5, any scalar value. And then once we apply the sigmoid to this resulting scalar value, we're going to get a probability between 0 and 1. Okay, so how will our multi-class classifier look like? Our multi-class classifier, again, it's nothing but a W transpose X similarly. So the only difference is that our W, our vector of weights, is no longer a vector. Now it's a matrix. Why is it a matrix? Because we have multiple classifiers. We have a cat classifier, we have a dog classifier, and we have a bird classifier. So we will have a matrix representing the weight for the cat classifier with pixel 1, the weight with the cat classifier with pixel 2, all the way to the weight of the cat classifier with the last pixel. Okay? And similarly, we will have the weights of the bird classifier with pixel 1 all the way to the weight of the bird classifier with the last pixel. So this is our W function. Again, we're going to apply W transpose X. This will generate a vector now. It will not generate a scalar value like in the binary classifier. Now it will generate a vector because this is a matrix multiplied by a vector. So the result will be a vector. Z1, Z2, all the way to Zn. Each element in this vector represents the score or the prediction W transpose X, so W cat transpose X, W dog transpose X, and W bird transpose X. Okay, this is how what our values Z are here. And again, these are just scalar values. To convert them into probabilities, what we can do is try to apply the sigmoid function. So we can apply the sigmoid function to all of this. If we apply the sigmoid to W transpose X, we apply the sigmoid to those scores. So the result will be, we said that the sigmoid is an element-wise function. So it's going to be sigmoid of Z1, sigmoid of Z2, sigmoid of Z3, and so on. Okay, let me erase, put some room here. Okay. So now, how will our results look like if we apply the sigmoid on Z1, Z2, and Z3? It will look something like this. We'll have 0.8, something like 0.4, and something like 0.6. And these will be our predictions, P cat, P dog, and P bird. Now, the problem is this does not look like a probability distribution. And why does it not look like a probability distribution? Because we know that a probability distribution is always between 0 and 1, and it always sums up to 100% or 1, right? So all of the probabilities here are between 0 and 1, and that is correct, but their summation does not add up to 100%, or does not add up to a 1. So we need a way to generate a probability distribution that is normalized, where all the values here are between 0 and 1, and the summation of all of the values are equal to 1. And this is exactly why we need to use a softmax function, which generates a probability distribution in a normalized fashion. This is how it looks like. So what the softmax function does is that it takes those scores, we'll call them Z's here. Let me grab the pen. So this is our score Z, and this will be our prediction P. So we will have, let's say we have a vector of scores here, 1.3, 5.1, 2.2, 0.7. So this is really Z1, Z2, Z3, and so on. So let's say Z1 is 1.3, Z2 is 5.1, and Z3 is 2.2. What the sigmoid function, what the softmax function does really is that it takes the Z scores and it exponentiates them, projects them onto the sigmoid function. So this is how Z1 looks like, Z2 looks like, and Z3 looks like. Okay, and then it will take the proportion of this height with respect to the sum of all heights. So if we add this height to this height to that height, this will be a very long line here. Okay, this is the just adding up all of these heights together. So what the softmax function is doing is that it's taking e power zi, so our zi here is e power 1.3, and it's dividing it by the summation across all of the heights, e power 1.3 plus e power 1.2 plus e power 1.5. So this is e power 1.3, this is e power 2.2, and this is e power 1.5. Stack them up over each other, you get this summation, which looks like this. So the resulting probability will be the proportion of this exponentiation of the total, and the proportion of that exponentiation with respect to the total, and the proportion of this exponentiation with respect to the total. So really, the softmax of Z1, Z2, and Z3 will be equal to e power Z1, which is this exponentiation, divided by e power Z1 plus e power Z2 plus e power Z3, which is this long line here, the addition of all of the exponentiations. And for Z2, it will be e power Z2 over, again, the summation across all of the Zi's. And for the last one, it will be e power z3 over the summation of all of the zi's. So as you can see here, we are normalizing the probability between 0 and 1, and the summation of all the probabilities will also add up to 1. Why? Because we have done it in a normalized way. And we are taking the proportion of e power zi to the summation of all of those probabilities. Okay? So this is what the softmax function is doing in a simple way. Okay, so how do we go about taking the derivative of the softmax function? So this is our softmax function. It takes as an input our z vector. So this is z1, z2, z3, z4. z1 is nothing but w1 transpose x. Let's say this is like w cat transpose x, w dog transpose x, w bird transpose x, and so on, w elephant, w giraffe transpose x. And what the softmax function is doing is that it will exponentiate this element, which is z1, and then it will divide it by the summation of all the exponentiations of all the other elements. So it will be e power 1.3, it looks like this, e power 1.3 divided by e power 1.3 plus e power 5.1 plus e power 2.2 and so on, plus e to 1.1. Okay, all of this is just to calculate the score S1. And again, for S2, it will be e power 5.1 divided by e power 1.3 plus e power 5.1 plus e power 2.2 and so on. This is to calculate S2. Okay, so how will we go about calculating the derivative of the softmax function? I hope I'm saying softmax correctly. I always get confused between softmax and sigmoid. So what is the derivative between the softmax function with respect to z, the input? Okay, so softmax function is nothing but s1, s2, s3, s4, and s5, which is a vector varied function because it returns a vector, and z itself is a vector. So we are taking the derivative of a vector varied function with respect to a vector. And if you remember from our matrix calculus video, the derivative of a vector varied function with respect to a vector is a matrix, right? So what will be our Jacobian matrix? It will be partial S1 by partial Z1, partial S2 by partial Z2, all the way to, partial S1 by partial Z2, all the way to partial S1 by partial Z5 in this case. And the last element will be partial S5 by partial Z5. This will be our Jacobian matrix. Okay, so why do we need to calculate the gradient of S1 with respect to Z1, S1 with respect to Z2, S1 with respect to Z3, S1 with respect to Z4, and so on? Because for a small change in any of those elements, S1 will change. Why? What was S1? It was nothing but e power Z1 divided by e power Z1 plus e power Z2 plus e power Z3 and so on. So if e power Z2 changes, the denominator will change, which means the entire S1 will eventually change and so on. So that's why we need to understand, for a small change in any element in the Z matrix, in the Z vector, how will that impact S1 and how will it impact S2 and how will it impact S3 and so on. So one small change here will change the entire resulting vector. And that's what we're trying to calculate here. Okay. So to simplify this, we're going to only be dealing, instead of calculating each derivative separately, we're going to generalize this and say we are calculating partial of Si with respect to Zj. Okay. This is I and this is J. Si is basically S1, S2, S3, S4 until S5, and Zj is Z1, Z2, Z3, Z4, Z5, right? So we're calculating partial, and this element here will be partial S1 by partial Z1 for I equal 1 and J equal 1. The last one, I and J are equal to 5, so it will be partial S5 by partial Z5. An intermediate element could be something like partial S2 by partial Z3, for example. So our generic gradient we're trying to calculate here is partial Si by partial Zj. What is Si? This is exactly what Si is, right? because what SI here is doing is taking ZI, exponentiating it, and it's dividing it by the denominator. So SI is this equation up here. It's to calculate S1, S2, and S3, and S4. It's basically calculating SI. So SI is this equation. So what we want to do is take the partial derivative of SI, which is e power ZI over sigma e to the ZJ with respect to ZJ. This is the derivative we are trying to calculate, or to calculate the derivative of this element here. Okay, so how will we go about doing this? Okay, so again, what we're trying to calculate here, let me grab the pen. What we're trying to calculate is partial derivative with respect to ZJ of SI, which is e power ZI over summation of all of the other exponentiations, j equal 1 to k. Okay, let's do this. So first of all, we will fix the numerator and take the derivative of the denominator. So it will be e power ZJ squared, the negative will come outside, and multiply by the derivative of what's inside. What will be the derivative of, so what is the derivative of sigma e to the ZJ? To answer this question, let's expand it, okay? So let's assume that this is e power Z1 plus e power Z2 plus e power Z3. And here we are trying to calculate d by dz1, for example, of this summation. What's d by dz1 of this summation? This is 0, 0, and we will end up with e power z1. Okay, what's the derivative with respect to z2 for this summation? Is nothing but e power z2, because the rest will be zeros. Derivative of z3 for this summation is nothing but z3. So basically the derivative of zj with respect to this summation is nothing but e power zj itself. Okay, now we have taken the derivative of the denominator. Now we fix the denominator, which is this one, we fix it, and we take the derivative of the numerator. What's the derivative of the numerator? Derivative with respect to zj. Remember, all the derivatives we're trying to calculate here is with respect to zj, right? So this is partial si by partial zj. So we're going to take the derivative with respect to zj of e power zi. Okay. So what is the derivative of e power zi with respect to zj? The answer is we don't know, because it will differ. What if, so imagine you're taking d by dz1 of e power z1. What's the derivative? Well, it's simply e power z1. But what if you're taking the derivative of e power z1 with respect to e power z1 with respect to z2? What will be the derivative? It will be 0. So depending on I and j, this resulting derivative will be different, which means we need to split this problem into two problems, right? So we're going to take the first problem here, which is, let's assume that I is equal to j. So if we look back at our Jacobian we're trying to compute, this is I and this is j. So I equal to j means we are looking at the diagonal elements of this resulting Jacobian. So what is partial d by dzj when I is equal to j for negative e power zi e power zj over, I'm just going to expand the summation into two brackets. So I'm just gonna make it sigma e to the zj multiplied by sigma e to the zj. Just converted the power 2 into two brackets, and then plus, here our derivative was 1 over sigma e to the zj multiplied by the derivative of e to the zi with respect to zj. When I is equal to j, it's as if I'm saying what's the derivative of e power zi with respect to zi, because I is equal to j. So it's this situation here. When I is equal to j, it's nothing but e power zi itself. So this will be, get the pen again, e power zi over sigma e power zj. Okay, now this is actually the gradient itself. We're not computing, this is the gradient. So let me erase this to make it look better. So yeah, so this is partial si by partial zj is equal to this. Fantastic. Okay, can we simplify this? Well, yes, we can. Remember, this is nothing but the softmax of I, right? This is nothing but Si itself, e power zi over what sigma all the zj's, e power zi divided all of the zj's. So this is nothing but the softmax I. And this is also nothing but the softmax I, right? It's the same, e power zi divided the summation of all of the other exponentiations. So this is Si, this is Si, and this is nothing but Sj, right? Sj, because this is e power zj divided summation of all of the zj's, so it's nothing but Sj. So the resulting gradient, e power partial Si by partial zj, is equal to negative Si Sj plus Si, right? Which can be simplified to Si multiplied by 1 minus Sj. So all the elements on the diagonal will have this value. Si multiplied by 1 minus Si, Si multiplied by 1 minus Sj. So this is in the case when I is equal to j, which is the diagonals. Let's take the other case, which in my opinion is the simpler case, when I, let me grab the pen, when I is not equal to j, which means we are calculating all the elements outside the diagonal. So again, our derivative here was partial e power zi with respect to zj when I is not equal to j. So this is the second example here when we're taking e power z1 with respect to z2, which is 0, which means this entire term will be 0, which means this entire term will go away. So we'll end up only with this one, the first term. So the resulting gradient will be nothing but, grab the pen, will be partial Si by partial Zj when I is not equal to j is negative e power zi e power zj over summation e power zj multiplied by the summation of e power zj. And from the previous example, we said that this is zi and this is this is si and this is sj. So this entire thing simplifies to negative si sj. So the derivative of the softmax at any element that is not on the diagonal is negative si sj, where I and j are the indices of the matrix, I and j. Okay, so let's put it all together. The softmax function, the derivative of the softmax function, so partial si by partial zj is equal to si multiplied by 1 minus sj when I is equal to j, and it's equal to negative si sj when I is not equal to j. Okay, so the entire Jacobian will look like this. Partial s by partial z, which we're trying to compute, this entire big Jacobian will be, this is the diagonal, these are the diagonal elements, so it will be s1 multiplied by 1 minus s1, because here I is equal to 1, j is equal to 1, so s1 multiplied by 1 minus s1, and this is an off diagonal element, so it will be negative si, I is equal to 1, so negative s1 multiplied by sj, j is equal to 2, so negative s1 s2, negative s1 s3, and so on. Here it will be negative s2 s1, and then the second element is a diagonal element, so it will be s2 because I is equal to 2 multiplied by 1 minus s2 because j is also equal to 2, and then the off diagonal elements will be negative s2 s3 and so on, and the here this is the last element. It will be S5 multiplied by 1 minus S5, and the element before it will be negative S5, S4. And this is how your Jacobian of the softmax function will look like. Oof, it was quite a tedious proof, but I hope you understood it and enjoyed it. If you have any questions, please leave them down in the comments below. Thank you for watching the video. I hope you enjoy it, and see you in the next video.